Okay, so here are the exam scores for the 15 students in Mr. Kirk's stats class. Karen was at the 20th percentile, so you want to take 0.2, which is 20%, times the total number of students, which is 15. So we find 3. So you're looking for 1 to the third student. So that would be the student at the 20th percentile. Consider the following cumulative graph. Students earn a score of at least 80, win 5 tickets. What percentage of students who played skee ball won 5? So score is at least 80. So like all of these folks are at least 80. So how often does that happen? 20% of the time. Because it's from 80, you see those folks are between 80 and 100 there. So it's not 80% of the time. 80% of the time, a student gets a score of 80 or below is the meaning of percentile. So 80% of the time, a student gets 80 or below. So it seems like we're gonna have to do some z-score stuff here. So we're comparing two scores that are not on the same scale. So remember the z equation. So z equals the value. Let's see. So Carrie's mean score is that with a standard deviation of that. Carrie gets a score of 14,000. Okay, so it'd be 14,000 is her value minus the mean of 12,400 over the standard deviation of 1,500. That's going to equal something. And then Vicky has a z-score. Let's just work these out in just a second. Of so mean is 14,200. That, and she gets 16,000. So 16,000 minus 14,200 over 2,000. So figure out the z-scores here. So the first one would be control divide, so 14. Put a decimal in there so I get a decimal. So I get a z-score of 1.066 standard deviations above the mean. And then I'm going to do Vicky's, which is 16 minus 14 all over 2,000.9. So who had a higher z-score? So this was 1.06. This was equal to 0.9. 1.07. So Carrie, so we know it's one of these guys. 0.9, so Carrie wins the contest. So we're just comparing z-scores because the scales were not quite the same. Distribution of data is normally distributed with the mean of 25 and standard deviation of 8. I'm not sure if I have to do this, but I typically just start drawing. So 25, so I go up 33, up 8, 41, I think, and 49. And down 8 would be 17, down 8 is 9, and down 8 is 1. If you calculate the standardized score of every observation of the data set, what will the mean and standard deviation of the resulting scores be? Okay, so if I do the standardized score, so when it says standardized score, you got to be thinking to yourself z-score, right? So z-score, if I did z-score for everything there, what's the z-score for the mean? Always, it's 0, right? What's the z-score for this one? 1, 2, 3, -1. That was so fast. I did all that calculation. Those are always the z-scores, right? So now I have it in terms of z-scores. So what is the mean? Always 0. It's the default when you do norm CDF, right? And always standard deviation of 1. The normal curve describes the death rates from heart disease per 100,000 people in developed countries. The mean and standard deviation have approximately what values? So the mean is definitely 200. approximately. So it's one of these guys. Those are gone. So we know between the mean and the last number there, where the data pretty much ends, it's going to be 3 standard deviations. So between 200 and 400 is 3 standard deviations. So I think I'm going to subtract those two. You can probably do that in your head. And divide that total by 3. We should get our answer. Whatever 200 divided by 3 is, my guess, strong guess, is that that is 67-ish. So we're going to go with C. These can be tough. Let's just kind of look at it and see which one makes sense. So the area under a normal curve is always 1, regardless of the mean and standard deviation. That is absolutely true. So it's always 100%. Area under the curve is always 1. So I know 1 is true, which means this one's not logical, and this one also is not logical. It's got to include 1 as part of the answer. The mean is always equal to the median for any normal distribution. So they didn't say approximately normal, they said normal. So is that true? Is it exactly equal? Yes, it is. For a true normal distribution, that's going to be true. So now I know that guy's gone because it doesn't include 2. Okay, got to check 3 still. The IQR for any normal curve extends from 1 standard deviation below the mean to 1 standard deviation above the mean. So I think you're getting confused here. They're getting confused. So that would contain 68% of the data within 1 standard deviation, but that is not where the IQR, where the Q3 and Q1 are. So I don't think 3 is true, so it's got to be A. The heights of American men aged 18 to 24 are approximately normally distributed with a mean of 68 and standard deviation of 2.5. Again, I usually just start drawing this. Last time I didn't really have to, I guess, but 68, 2.5. And if you're having trouble doing that, if you want to do that in your calculator, again, the best way, type in 68, press enter, hit plus 2.5, and press enter 3 times. 70.5, 73, and 75.5, I believe. And again, if you're having trouble with decimals, it's just not easy. 68, subtract 2.5 3 times. So 65.5 and 63, 65.5 and 63, and 60.5. Okay. About 5% of young men have heights outside of this range. So the key thing, I think, it says outside the range. So 95% would be inside the range, right? Well, 95% is 2 standard deviations from the mean, right? Is 95% of the data is in between that. So I think it'd be between 63 and 73. 63 and 73, there it is. At the height of 99.7, that's an interesting choice. It's one of the numbers from the empirical rule. Between 5 and 7, what is your estimate for the standard deviation? So how can I draw this? So we got way out here, we've got, 5 and 7, and the mean somewhere in between, probably a 6, by the way, right? What is your estimate of the standard of the height of American men? So 99.7. So between here and there, right, is 3 standard deviations. So dividing 1 divided by 3, 1 foot divided by 3, which is 1/3 of a foot. What's 1/3 of a foot? 1/3 of 12 inches is 4. So I think it'd be that. You can also take the difference between 7 and 5 is 2. So 2 divided by 6, 2 feet divided by 6 is, again, 1/3 of a foot, which is 4 inches. X denote the time it takes for a computer link to be made between the terminal in an executive's office and the computer at a remote factory site. It is known that X has a normal distribution of the mean of 15 and standard deviation of 3. I'm going to draw it again. It's just a habit I have that usually serves me well. 15, so then 3, so that'd be 18, 21, and 24. It's really sloppy, but that's okay. 12, 9, and 6. Okay, on 90% of the occasions, a computer link is made in less than how many seconds? So 90%, so somewhere like, I don't know, over here is a point that if I shade it, I'm just kind of like 90% would be to the left of that point. I'm not sure exactly where that point is. I'm call that point X or something. So I know the percentage and I want to find the value. So what command do I use if I know the percentage and I want to find the value? So you got menu 6.5. I don't think that's norm CDF. We need to know the values there. Let's go inverse norm, 0.9. Instead of leaving it default 0 and 1, let's go ahead and put in the mean and standard deviation here, which are 15 and 3. So it should be 18.8. There you go. The mean score for the stat test was 68.5. Standard deviation was 15.4. So let's just kind of, again, I just get in this habit. It's not a bad idea to picture it. 68.5. So it looks a little tougher. I'll go ahead and use the calculator. So 68.5. Press enter. It's plus 15.4. 3 times we press enter. So we get 83.9, 99.3, and if I go to the third standard deviation, which is 114.7, and then 68.5, press enter, minus 15.4, press enter 3 times, 53.1. 37.7, 22.23, or something like that. Okay. It says, which is probably as closest to Daphne's z-score. So Daphne's score is 58. Well, that's like, I don't know, somewhere in here is 58. So right away I know it's z is going to be negative. And it's between 0 and 1, because 53.1 is 1 standard deviation below the mean, and the mean is 68.5 is the mean there. So I know it's negative, it's less than 1, so it's got to be one of these guys for sure, I think. Okay, so how do we get this? All right, so I want to find the z-score. So I'm going to try. I mean, let's just use the equation, right? Let the equation do the work. So it says the value is 58 minus the mean is 68.5, and the standard deviation is what was it? 15.4. So if you type that in, you get 58 minus 68.5 over 15.4. Negative 0.68. And that's the answer. It is okay that they were skewed left. I think some students will kind of like go, wait a second, this is skewed left. I can't use z-score. You can use z-score. You can't use the normal distribution. You can't use norm CDF. You can't use inverse normal. You can only use z when it's skewed. So you can't use the normal model when it's not normal. So we're comparing, in this one, we're comparing two folks, like one is the 4-year-old car. So for the 4-year-old car, so the z-score would be, so it has 40,000 miles. So the value is 40,000 minus the mean of the 4-year-old car is 56.68. So that seems funny. This must be measured in thousands of miles. 40,000 miles. It's 40 there. Because I was like 40,000 minus 56 doesn't seem right. It helps to read stuff. So 17.82. We'll type that in a second. For the 3-year-old car, the z-score is equal to, so the value was 30,000 miles, so 30 minus, makes sense if we have less miles, it's likely, 33.33 over standard deviation of 12.7. And again, that should give us an answer as well. So you get your calculator out, and it'd be 40 minus 56.68 all over 17.82. And that one's negative 0.93. And the next one would be 30 minus 33.33 over 12.7, negative 0.26. How does the number of miles compare relative to cars provide to support your answer? How do they compare? So, the 3-year-old car is closer to the mean. It's only 0.26 standard deviation is below the mean, so it's closer to the mean. Is what we expect for a 3-year-old car. Whereas the 4-year-old car has less miles than we expected at 4 years old, because it's almost 1 standard deviation below the mean, so quite a bit less. So this might be the better deal mileage-wise, at least. Assuming the distribution of mileage is approximately normal for 4-year-old cars, estimate the number of 4-year-old cars that Lamar looked at that had been driven more than 42,000 miles. Okay, so we're looking at 4-year-old cars, right? I'm just kind of sketching it out. We know the mean is, for 4-year-old cars, is 56.68. And 42 is somewhere over here, driven more than 42. So somewhere over here is the number 42. And we're kind of shading to the right of that. And again, the standard deviation is, for a 4-year-old car, is 17.82. So I think we have enough to do. We know it's normal. It was given to us. So get your calculator out. Go to the trusty old menu 652, norm CDF that guy. It's going to start at 42. Go to infinity, or a really big number. The mean was 56.68. The standard deviation was 17.82. 0.79. So 79. Let's see. That's an option. Oh, it's 0.794, 5 is the answer. What are the units of that one? So estimate the number of 4-year-old cars. So that's the percentage, but he looked at a total of 30 cars, it says. So I'm going to multiply that by 30. So 23, about 24 cars. Let's see what they say for this, but in a second. About 24 cars that he looked at had been driven more than 42,000 miles. The other thing you want to do here is so this command here, norm CDF, so norm, you need to show your work, CDF. The lower was 42, lower was 42, upper was infinity or something like that. Mean was 56.68, I'm running in a room, and standard deviation was 17.82. So showing that work is great. We love to see a little sketch there, but sketch is not necessary if you don't have to. Estimate the 60th percentile for mileage on cars found that were 4 years old. So again, we're looking at the 4-year-old one. So the command we need when we start with the percentile there is going to be menu 653, which is inverse norm. Type in that percentile was 60, so 0.60. The mean was 56.68, and the standard deviation was 17.82. Should do it for us. 61.1946. What's the question asked for? Estimate the 60th percentile. Let's see, does that make sense? Oh, mileage. So that means 61, about 61,000 miles. And again, you want to show your work here. So you want to say inverse norm. When inverse norm CDF or inverse norm, always show your work. 56.68 and 17.82. And that's going to be the area. That's going to be the mean. And that's going to be the standard deviation. Just want to make sure we got that one about right. So let's look at 11 answers. So there are answers on this sheet. So good. About 79% of the cars were driven more than 42,000 miles, or about 24 cars. Is that what we said? About 24 cars. And then part C, the z-score for this is 0.25. So 61, I rounded it a little bit, but I think we got the idea. 61.1 thousand. Yeah, that's basically it. Yeah, that'd be a little more accurate. Okay, number 12. The Dow Jones average. Okay, so 2016 is approximately normally distributed. So I'm just going to kind of sketch it out. Really bad sketch here. Negative 0.198. Definitely need my calculator for this one. So negative 0.198, press enter, hit plus. Standard deviation, which is 2.331. Press enter 3 times. So you get, oh, I did not do that right. Okay, so negative 0.198. And then I'm going to put plus 2.331 3 times. So I get 2.133, 4.464, 6.795. Press enter, subtract 2.331. So negative 2.529, negative 4.86, and negative 7. I don't think you need that 0.191. Okay. The question is, estimate how many of the 61 days the Dow decreased by more than 1%. So it went down, so that's negative. So somewhere in here is the negative 1%. So I want to find out how many days it was by more than that. So like you've got it, you're shading to the left here, to that -1 area. So this is a norm CDF problem. Seems to be a normal curve here. So menu 652, negative infinity is default. That's fine. -1. Mean is -0.198, and standard deviation was 2.331. So we should get 0.365401. Okay, so on 36% of the days, it decreased by more than 1%. It's kind of scary, right? But you got to think about the other way, like it increased quite a bit too. So it might have been okay. Stock market's kind of a wild ride in the short term. Okay, so we've got our answer. You want to show your work, so norm, CDF, show the things with the inputs. I'm not going to write it down, but I think you know what I'm talking about there. The standard distribution for 2018, so now we're talking about this guy, is norm with the 19th percentile of the daily change for the first 3 months of 2018. Estimate the 19th percentile. So the command we're going to use, we're using this mean and this standard deviation. The command you're going to use is inverse norm, right? And put the percentile in there. So the 19th percentile. So menu 653, 0.19, because that's that, or to the left, that's really nice. Mean is 0.078. Whoops. 0.078. Standard deviation is 0.821. Negative 0.64. Let's see what this question was asking again. Estimate the 19th percentile so it decreased by negative 0.64. It decreased by 0.64% for the first 3 months of that year. Just double check 12 and see if we got the right answers there. So 22 days. Did I answer the question of the first one? Assuming for how many days of the 61 days. So the thing I forgot to do is answer the question. So let's see if we got it right. So 0.365 times 61. 0.365 times 61 is about 22 days. So you should always just read the question to make sure you answered it. We did all the right work. We got the right number, but we didn't answer the question. Let's see if we did on the next one. So that's number 12, part B. So about a 0.64% decrease. We did get that one right. Okay, the average, this one looks pretty straightforward. Average temperature, so forth, you're going to convert the mean and standard deviation. Okay, so let's plug in. So the mean is affected by both, right? So I'm going to take 9/5. This is for the mean. So the mean is going to be 9/5 times the mean, which is 21.82, plus 32 in the formula. It's going to give you the answer when you type in your calculator. Standard deviation is going to be 9/5 times the standard deviation of 2.88. And you don't add 32 because adding doesn't affect standard deviation. So you just type those guys in your calculator. You should get the answer. Let's look at 13, see if I did it right. Yeah, you type it in, you get 71.24 and 5.184. Standard deviation is not affected by the addition of a constant. Okay, this one's similar to the other one we did. So it looks like 13 is in the middle. So the median is 13 and the mean. If it's approximately normal, those should be about the same. So they should be about that. From here to here is 3 standard deviations, right? From the mean to the point out there. So that's a difference of 10. right? So 10 divided by 3 is 3.33, I think. So I think it would be 3.33. Get your calculator if you want to, and you got it. That's your review.